Good morning, students. Dear students, as in the previous video, that is part 9 of the chapter 5 laws of motion, we had discussed about one of the application of equilibrium of forces, and we had discussed Lami's theorem. Now today we will be going to discuss the common forces in mechanics. In mechanics, what are the forces commonly used? That forces we will discuss in today's video lecture, that is common forces in mechanics. So today we will discuss about common forces in mechanics. Common forces in mechanics we will discuss. Dear students, when we are going to talk about the common forces in mechanics, then we can classify the forces in mechanics in two categories. First one is non-contact forces. Non-contact forces. Now we will ask what are non-contact forces. So non-contact forces are those forces in which the forces are going to act between two bodies, two interacting bodies, but the two interacting bodies are not in actual contact with each other. Means you can say that these are the forces. These are the forces which acts between two interacting bodies such that the two bodies are not in actual contact with each other. Means these type of forces, they are the forces in which the two bodies are not in actual contact with each other, and such type of forces are called as non-contact forces. Now dear students, let us discuss one of the non-contact forces which are generally used in mechanics, that is the one and only one force in mechanics is gravitational force. In mechanics, one and only one force which is of non-contact nature is gravitational force. Gravitational force. And this is the gravitational force due to which any body on the earth is attracted towards the earth due to gravitational force. much aware that in gravitational force, I'm just giving a brief idea. In gravitational force, suppose this is mass m1 and this is mass m2, and these two masses are separated by a distance r. Then these two masses m1 and m2 are not in actual contact with each other. In spite of this, there is a force of attraction between these two masses m1 and m2, and that force of attraction is the gravitational force of attraction, and it is given by F is equal to proportionality constant, that is gravitational constant G, into m1 m2 upon r square. So this is the only non-contact force in mechanics, and non-contact forces are those type of forces in which the two bodies which are interacting, or you can say that the two bodies which are exerting force on each other does not are, or you can say that are not in actual contact with one another, and such type of force is called as gravitational force. And it is the example of gravitational force is the example of non-contact force. Now we will discuss about the contact forces. Now we will discuss about contact forces. Dear students, contact forces are those forces in which, as the name implies, as the name, from the name you are getting the idea. Second one is contact forces. Contact forces. Contact forces. What are contact forces? Contact forces arises due to these forces arises due to the actual contact between two interacting bodies. Actual contact between two interacting bodies. When there is an actual contact between two interacting bodies, then it gives rise to the contact forces. So, apart from the gravitational force, rest of the forces which we commonly discuss in mechanics are the contact forces. Now, one by one, we are going to discuss about the contact force. For example, first example, we are discussing about the contact force. Suppose it is a book. It is a book, and this book is kept. This book is kept on the table. This is book, and this is kept on the table. This book is kept on the table. So the forces. This is the weight mg, and there is a normal reaction which counterbalances the weight of the book in such a way the book is in equilibrium and the net force on the book which is kept on the table is 0, and book remains at rest on the table. So look at here, this force arises due to the contact of the book with the table. If the book is kept on the table, due to that contact, the normal reaction arises due to the attraction of the book towards the earth, that is weight mg, and the normal reaction, and if this normal reaction is denoted by. The second example is, suppose this is a table, and here there is mass m1 and there is mass m2, and they are connected by a rod. Then if a force is applied on mass m1, then due to the Newton's third law, a tension is being experienced in the rod connecting the two rigid bodies, that is masses m1 and m2. So these are the mutual contact forces for each pair of bodies satisfying third law, Newton's third law. These forces are mutual interaction forces satisfying Newton's third law. Satisfying Newton's third law. Here they look at here the normal reaction and the weight energy. These forces arise due to the mutual interaction between the tabletop and the book, the surface of the book. Here also a force F is pulling mass m1. These are two rigid masses, so the rod connecting these two masses, due to the Newton's third law, a tension is arising here, and due to this tension it pushes mass m2. So counterbalancing this tension, a tension is experienced by this block also. So these forces arises due to the mutual interaction between the two bodies when the external force is applied, and it is due to the Newton's third law that every action has equal and opposite reaction. Now this is the case of the solid. Now in liquids also, when solids are in contact with fluid. Third example we are taking. In fluids also, fluids means what? Fluids are those which can flow, and in the latter chapter, that is second part of second volume of class 11, you will study about, complete a study about fluid mechanics, and in that we will discuss all these things. So when a solid is in contact with the, when the solid is in contact with the fluid, when the solid is in contact with the fluid, and when there is the solid in contact with the fluid, then I am taking an example. Suppose this is a glass tumbler which is filled with water. This is a glass tumbler and this is filled with, this is the glass tumbler and this is filled with water, and if a block is inserted, if a block is inserted in this glass tumbler, then a weight mg is experienced by this block, and there is a force exerted by the liquid on this block. That force is called as buoyant force. Buoyant force. And this buoyant force buoyant force is equal to weight of liquid displaced by weight of the liquid displaced by the means when a fluid is interacting with the solid body, when the fluid is interacting with the solid body, then it displaces certain volume of liquid, and a buoyant force or upward thrust is experienced by this block, and that upward thrust is called as buoyant force, and this buoyant force is equal to the weight of liquid displaced by the what about the weight of the liquid displaced by this block? That according to Archimedes principle, that weight of the liquid is equal to the buoyant force which can be experienced by this block. Second, in the same scenario, second example we can take. Suppose here there is a flowing water, and if you are moving a rod in this direction, water is flowing in this direction, and if you are moving a rod or exerting a force on the rod in this direction, then there is the hurdle or a resistive force experienced by you. That force is called as viscous force. Or you can say that if there is a bucket filled with water and a ball is inserted here, then due to the liquid layers, a force is experienced in upward direction due to the weight of the ball inside the liquid, and this is called as the viscous force. This force is called as the viscous force. A resistive force which is experienced by the moving object in the fluid. Similarly, you can say that when you are driving your bike, when you are moving your bike against the direction of wind flowing, again if wind is flowing in this direction, you are driving your bike in this direction. In that case also you will feel a resistive force by the moving air, and that resistive force is only due to the interaction of your body with the flow of air or fluid in which you are moving. So these are the examples of interaction of a body with another body, a type of contact force. These forces are due to the contact force. Clear, students? Now next we are going to discuss force due to spring and force due to string. Dear students, I am talking about this type of forces because when you are going to solve the further numericals, and in that numericals there is a free body diagram, such type of forces come in contact with you, or such type of forces are used in the numericals while solving that numericals. So you must have the idea about these type of forces. So we are going to discuss this type of forces here. Now let us say third case, force due to spring. Force due to spring. And what about the force due to spring? Suppose we have taken a top and in that we had tied a spring, and the spring is attached with the block of mass m. The spring is attached with the block of mass m, whose weight is m. Then what will happen, students? When weight mg, you had seen the spring balance. This is similar like the spring balance. And when in case of a spring balance, a weight m is attached to it, it elongates the spring. It elongates the spring, means the length of the spring starts elongating. That is, then what will happen if the length of the spring starts elongating? Then a work is done in stretching this spring, then a restoring force is developed, which tries to pull the spring in its original shape. It tries to pull the spring in its original shape, and so there is a restoring force against elongating force. The restoring force against the elongating force, which tries to elongate the spring, and that restoring force is directly proportional to elongation. If this spring is elongated with the displacement x in vertical direction, then the restoring force is directly proportional to L, and F restoring, it is equal to K into X. F restoring is equal to K into X, where K is called as spring constant. Dear students, we will discuss all this phenomena quite in detail in the next chapter, that is work, energy, power, and in that we will discuss about the energy, all the type of energies, potential energy, kinetic energy, total energy in stretching the spring. We will derive there also. K is called as spring constant, and X is the elongation produced in X is the elongation produced in the spring. X is the elongation produced in the spring. So, dear students, when a spring is compressed or extended by an external force, a restoring force is generated. This restoring force F is usually proportional to compression or elongation. That is a small distance. This is the case of elongation. If we compress it, then restoring force X. If we are applying the force to compress it, then restoring force X in downward to elongate in its original position. And here also the compression force is directly proportional to X, and F compression is equal to K into X, where K is the spring constant, just opposite to this. So this is all about the force due to string. Now the second case we will discuss about. Here we have taken the case of the spring. Now if we take at the place of the spring, we take string. If we take a string, S-T-R-I-N-G, here a string, now force due to string. Now dear students, we will discuss about force due to string. Force due to string. And here we will take the Suppose this is a ceiling, and from this ceiling we had tied a string, and from here we had loaded a mass M with the string. Then there is the weight mg. Due to the gravitational pull of the earth, there is the weight mg and a tension T acts to counterbalance the weight mg. So, according to Newton's third law, T is equal to mg for the case of equilibrium. If it is the mass mg is tied with this string and the mass m is at rest, then the tension produced in the string counterbalances its weight in such a way that T is equal to mg. T is equal to mg, where T is equal to tension produced in the system. So, dear students, we can say that when a body of mass m is fastened with the string, then the weight of the body acts downward, while a force acts just opposite to the downward force for balancing the downward force, and this force is called tension. So we can define tension here also. Tension, a force which acts in the string to counterbalance the force, counterbalance the weight mg of the block which acts in downward direction. This is called as the tensor. This is called the tensor, which is produced to counterbalance this weight. So, dear students, I think it is clear to you about the force due to spring and force due to string. Now, we are going to discuss about free body diagram. What is free body diagram? Free body diagram is nothing, students. Free body diagram is just the representation. It is just free body diagram. First of all, I am writing the heading free body diagram. Free body diagram. Free body diagram is just a diagram which represents all the forces which is acting on the body. The diagram which represents all the forces which is acting on the body is called as free body diagram, and in that case the body is considered as the point object. As we had discussed about the point objects are those objects whose distance traveled is much smaller than the dimension of the object. When the distance traveled by the object is much smaller than the dimension of the object, then such type of objects are called as the point object. So while drawing the free body diagram, we will consider the object as the point object. So the diagram which represents all the forces acting acting on the body body is treated as a point object, when the body is treated as point, when the body is treated as point object, then what about the forces acting on the body? The diagram which is representing all the forces acting on the body is called as free body diagram. So let us understand this free body diagram with an example. Suppose we have taken this horizontal surface, and on this horizontal surface we have taken a block of mass, and this block of mass, and we will discuss about a force that is called as frictional force, and that frictional force you had studied in class 9th also. That frictional force acts opposite to the direction of the motion of the object, which opposes the motion of the object. So here we are considering a force parallel to the motion of the block of mass, and this is called as the frictional force F. Then there is a frictional force F also acting on this object, and we are pulling the object with a force F which is making an angle theta with the horizontal. Now we are interested to draw its free body diagram. So its free body diagram, its free body diagram that its FBD, free body diagram, can be represented as, suppose this is body of mass and we have considered it as a point object. Then look at here, the body is of mass m, so its weight mg x, and since its weight mg x, because the object is pulled by the earth due to gravity, so according to Newton's third law, this surface also exerts a normal reaction which counterbalances the vertical forces, because there is no any vertical motion. So in vertical direction these forces are going to cancel each other. Now a force F is acting, making an angle theta with the horizontal. So we can resolve this, since force is a vector quantity, so we can resolve this force into its two components, that is the horizontal component and vertical component. So its horizontal component F is F cos theta, and its vertical component in vertical direction is F sin theta, and another force, that is frictional force, in this direction. So this is the free body diagram for, we have dissolved the force into its two components, its normal reaction weight mg and this force F. All the forces we have represented in a single diagram. So you can say that this is the free body diagram. Now if the body, according to the question, if the body is in equilibrium, under the action of these forces, then we can do what? We can make an equation, summation of fx, all the forces in x direction. So x direction, all the forces f cos theta and minus theta. So we can write it as f cos theta minus frictional force, and it is equal to 0, because there is no any motion in the horizontal direction, it is given. And summation of y component, this is the vertical force, this is the y direction, this is the horizontal direction. So in horizontal direction we have taken f cos theta minus f cos theta is in this direction, positive direction, and frictional force in this direction, that is negative direction. So we have taken as f cos theta minus f is equal to 0. And now the vertical forces Fy can be written as, look at here, two forces are in upward direction. So we can write it as R plus F sin theta minus mg, and it is equal to this in this way we can make the two equations from this free body diagram, and we can solve according to the question and get the values whatever required. So dear students, this is all about for today discussion. In the next video we will discuss about 2 or 3 numericals based on the free body diagram, and then we will discuss the further topics. Thank you students. Have a nice day. Take care.